This week we're going to be working on Chapter 9, which looks at single sample hypothesis test. I broke this video up into two parts, hoping that maybe it would help. In part 1, we're going to talk about hypothesis testing in general, some risks that you run by doing them, and we're going to look at developing hypotheses for means using normal distributions, which of course means that we're assuming that we know what the standard deviation is. In part 2, we'll look at t-tests and proportions and developing hypothesis tests for those measures. Anyway, what I did is, and I need to move back up, I tried to just kind of set this up so that you can kind of follow through the notes, and I will try to get these posted. Number one, when you're doing hypothesis testing, it's very similar to what we did back in 7 and 8 when we looked at sampling distributions, which of course is the underpinnings theoretically for our hypothesis test and also for interval estimation. And then our interval estimates or confidence intervals themselves are kind of, to me, another way to look at the same data. Remember, in our confidence intervals, what we did is we thought we knew what's in the population. We took a sample and then we compute a range of values based on this confidence level that we have chosen, that it gives us an upper and a lower boundary, and we're just asking whether what's in the population fits in there or not. In hypothesis testing, you still think you know what the population measurement should be, but you're now taking a sample and you are going to determine whether the sample you took was close enough to your actual population measure to say that nothing's changed or it's within the range, or whether it's too far away and you have to say something is different. We'll kind of look at these, but you basically have two things. So you have a null hypothesis and an alternative hypothesis. In the null hypothesis, the HO, this is a statement that nothing's changed. This is what we thought is there, and nothing's different from that. The alternative hypothesis, which always has to go with it, is the opposite, and this is where your research question comes in. So your research question says, is something different? That's where you would state that would be in the alternative hypothesis. We'll look at the forms and the mathematical operations and things a little bit later. There are some risks to taking samples, and he presents a table, table 9.1 in your book, where he looks at potential types of errors that can occur when you take samples. So these risks in decision making, number one, there's no way to measure whether these things have occurred or not. You just have to wait and see whether something shows you that they did. So you have to be very careful when you're looking at hypothesis testing and recognize these things could exist, but you'll never know exactly what they are. So for example, and I made up this example so we had something to talk about here. Suppose we manufacture children's car seats, and they have to have some impact resistance. So periodically we have to test some of the car seats to see whether they meet these impact standards, probably the government has set. And in this case, the null hypothesis would be some sort of statement that says our process is working exactly as it's supposed to. In other words, the car seats meet the standard for impact resistance. So we have no problem. The alternative hypothesis would be that the car seats that are being produced don't meet the standard, which means, yes, we're producing defective car seats. So in a type 1 error, which is sometimes called a producer's risk, we take our sample. Turns out we took the sample, but it's not really representative of what's in the population. So, and our sample tells us, when we took our measure, that the car seats do not meet the standard. So at that point, you get your sample back, you say, oh, I've got a problem, shut down my production process, I fix it. I do whatever I need to do to fix the process. But because this sample was not really reflective of what was in the population, what actually is happening is the population, the HO is true. You're actually meeting the standard. So I think of this as a wasted effort. You shut the process down. You try to fix something that really isn't broken, and you waste a lot of time and effort doing that. and you make adjustments, and then you start your process back up again. So that's kind of how that one works. The type 2 error, to me, is more serious. Sometimes it's called a consumer's risk. Oh, maybe that's a good term, I don't know. But in this instance, you take your sample from your population. Again, this population is unknown, and your sample says, there's no problem. Our car seats are just what they should be. So you continue producing the car seats and take no action. The actual case would be, in this type 2 error, however, that we're actually producing defective car seats to begin with. And in that case, we are shipping out defective car seats, and we don't even know it. We don't know it until they get out in the marketplace, or somebody else tests them for us, like the government, or somebody gets injured and you get sued. Maybe people start returning them, and you've got to make all kinds of adjustments then. So you're producing defective car seats that really are not safe, but you don't know that because you took the sample. Thing with this type 1 and type 2 error is you never really know what's in the population at any given time, so you're really not going to know whether these two things have occurred. But just a small risk, but just know that they're there as part of the whole sampling process. Second thing I want to talk to you about is using the methods for actually doing hypothesis testing. There are two of them. You can use something called a critical value approach, where you use the appropriate distribution and you develop a cutoff between the rejection and the non-rejection regions based on these distribution tables. So that's one method. The other method is something called a p-value approach, which we'll look at in a few minutes. But in this critical value approach, I think he's got the steps on page 278. First thing I think you need to do is determine which distribution you're going to use. You're taking a single sample, and your measures are either going to be a mean or a proportion. And you remember from chapter 8, if the mean is the measure, and you have a situation where you think that you can estimate the standard deviation based on past experience, then you just put the standard deviation in and that's what you assume. In that case, you could use a normal distribution. The risk of that, of course, is that do you really know what the standard deviation is in the population? And if you really don't know what the mean is in the population and you're doing a hypothesis test about it, my best guess is you don't really know what the standard deviation is either. So that one to me is more risky. The second would be your mean is a measure, and you are not going to assume that you know what the standard deviation is. They call this an unknown standard deviation, but all that means is that you just computed the standard deviation using your sample data. In that case, you use the t-distribution. And the third thing that you might run into is proportion as a measure. And in that case, as long as the sample size is large enough, you're going to use a normal distribution. These are the same rules we used or same things we looked at when we did confidence intervals in the last chapter. Second thing you've got to do is you got to figure out what level of significance and sample size you want to use when you take this sample. Both of those things are up to you, the researcher. Typically, the confidence level is usually 95%. And remember, our confidence level minus our alpha level, or confidence level subtracted from 1 will give you your alpha level. So the alpha level is what we usually look at as our level of significance. And usually, again, we use 0.05, although sometimes we have reasons for using different levels. Anyway, and sample size itself, you want to use a large enough sample. Remember that we had rules for proportions. The empirical rule tells us we've got to have 30 if we really don't know what the distribution is. But if we have reason to believe that, we can probably use normal distribution, then something smaller than 30 is okay. So again, you, the researcher, pick the level of significance and the sample size. The third step here is to use this level of significance and the proper distribution, and you state something called a decision rule. In other words, you're going to identify the reject and the do not reject regions given your distribution numbers. This provides cutoffs, critical values. Then you collect your sample data and compute this test statistic, and after you do that, you compare your test statistic to your decision rule. You state a statistical decision and then some sort of a managerial conclusion. No manager wants to be told that you should reject the null hypothesis. Their eyes glaze over and they want an explanation. They want somebody to tell them the car seats you were producing are defective or they're not defective. So, do not, just state the statistical decision, but state the managerial conclusion. When you do a hypothesis test, and you have for the mathematical operations always are the same. So it doesn't matter whether you're measuring a mean, normal distribution, t-distribution, or whether you're measuring a proportion. What will change will be the measure for the central tendency in the population. But what doesn't change are the mathematical operations. So if you have your research question says, has it changed? You're going to put an equals and a non-equals in for the alternative. If you're asking, has something decreased, then you are going to, again, that's the research question. It goes to the null hypothesis, the alternative, and you'll say, is it less than? And then the null would be, it's the same or it's actually increased. And then if you're asking, has something increased, your alternative will say greater than, and your null will say less than or equal to. We always use those two operations. The equality sign always is in the null hypothesis. So the first example using this, data on page 278, example 9.3 in your book, we have a situation where we think the mean in the population is 4.5. We think the standard deviation is 1.2. I think these are minutes of time people wait. And then from our sample data, we take a sample of 25. We compute a sample sample mean of 5.1 minutes, and we choose a level of significance of 5%. Our research question in this is something like, is there some sort of evidence that the time to place an order has changed? Change says equals and not equals. So you state your null hypothesis, you'll say mu1 equals 4.5. Your alternative will say mu is not equal to 4.5. You can leave the 1 off if you want to. As a matter of fact, I'll take that out right here, right now, because I don't need it. So anyway, your alternative is that it's actually not equal. So your critical value approach, what you do is that, once you've done all that, excuse me, you set up your decision rule using the appropriate distribution. Well, in our case, since we have estimated the population standard deviation, we use the normal distribution. Our alpha level is 0.05, which means we have 0.025 in the lower tail and 0.025 in the upper tail. And to find your critical value, you go to the normal distribution, you look up the area 0.0250, and you'll find a z-score of a negative 1.96. And then since it's symmetrical, we'll have a positive 1.96 as the upper critical value. So lower critical value is negative 1.96, upper one is 1.96. Anytime you get more extreme than these critical values, you're in the reject HO region. If you're in between them, you're in the do not reject HO. So we compute our test statistic using our sample data and come up with a test statistic of 2.50. That 2.50 is out here in this right reject region on the upper side, and we write our statistical decision as reject HO because our test statistic is greater than our upper critical value. In words, your managerial implication, managerial conclusion, you're going to tell your boss that the time to place an order has changed significantly from 4.5 minutes. Okay? Anyway, so be sure and state that also. And then we go down. The p-value approach, then, using the same problem, we got the same set of hypotheses. This is example 9.4 on page 283. That isn't right. 9.4 on page 281. 281. What we're looking at with a p-value is the probability of getting a test score that's equal to or more extreme than the one you get from your sample. So it is compared to the observed or it's actually the observed level of significance, and we compare that to our chosen level of significance to make our decision. So we have the same hypotheses with the same mu, sorry, of 4.5. So the null says our mean is 4.5 minutes. Our mu says, alternative says that mu is not equal to 4.5 minutes. Our decision rule, this decision rule works anytime you're using a p-value, so you just state that. So if your p-value is greater than our alpha level, then our decision is do not reject our null hypothesis. If the p-value is less than alpha, then we reject the null hypothesis. You can remember that decision rule, we'll be using it all semester. Our test statistic we already computed was 2.5. And then to get the tail area more extreme than that, you look up a z-score of 2.50 in your normal distribution, where you will find it's a right tail area of 0.9938. So to figure the area more extreme, equal to or more extreme than that, what you do is you subtract this tail area from 1, and that gives you 0.0062. Now, because the alpha is stated for combining both tail ends of the distribution, what we have to do is to double that area that we just computed, the 0.0062 multiplied by 2, to get the actual p-value. So our actual p-value is 0.0124, which is less than our alpha level of 0.05. Anytime you have a two-tail, you've got to double it. If it's a one-tail hypothesis test on the left or the right, you get an actual p-value. So anyway, that's the p-value approach. Pretty easy. pH stat. Let me show you in Excel how to do pH stat. I'm just going to go to a clean sheet. In pH stat, we said we know what our data is, and that's what we use to do our hypothesis test. So in this, you go to pH stat, and then you go to one sample test, and you'll see there are 4 of them. There is the normal distribution test for the mean with the sigma known. That means you guessed what it was. There's a t-test for the mean sigma unknown. That means you computed it from your sample. And then there's your normal distribution for the proportion. We're going to choose the first one. We didn't have a data set for this. They just gave us information. When it says null hypothesis, it's what it's asking is, what do we think is in the population? Our level of significance was 0.05, and our population standard deviation was assumed to be 1.2. And then you have 2 choices here. So if you had the actual data set, you would just tell it where the sample range is. But here we started out by saying we took the sample already, and we got 5.1 as the mean. I'm sorry, our sample size was 25. And then we got 5.1 as a mean. And we want a two-tailed test. You want to make sure you check the correct one. You'll get the wrong result if you don't. Because we asked if it had changed, we want a two-tailed test, and we say, okay, and there is your pH stat output. Anyway, so, and you can see the only thing you really, anybody looks at this point, once you get computer output, is the p-value, which is 0.0124. We just figured that by hand, and it even tells us to reject the null hypothesis. Of course, then you've got to explain what this means. Anyway, that's part 1. Hope that helps.